So let's take a quick little review of what we did on Friday with the graphing stuff. I told you on Friday that you will see on your diploma exam at least one question that has a graph on it. And you're going to have to find something from that graph to calculate something and put in an answer. It may be a graph that you've seen before. More likely, it'll be a graph that you haven't seen before. So how are we supposed to analyze that graph that we've never seen before? Well, that graph will take the form of y equals mx plus b because it will be a straight line. Okay, you will see a straight line graph that you have to analyze, and you know that equation that describes it is going to be y is equal to mx plus b. What do we do with this graph knowing that the equation is y is equal to mx plus b? Go ahead. Right, we plug in the y and the x values. So for instance, maybe we've got, I think we did this one on Friday. I'm trying to think of another example, but let's say we had 1 over di and 1 over do. Okay, 1 over di is a function of 1 over do. Let's replace the y-axis, or the y variable here, with whatever's on the y-axis. It becomes 1 over di, m is the slope. Let's replace x with whatever's on the x-axis. That's 1 over do plus b. What does b stand for, by the way? The y-intercept. Good. Make sense? Actually, that's a bad graph because this one should be more like this. Still a straight line, right? So it's still described by y is equal to mx plus b. All we've done so far, not much, all we've done so far is written down y is equal to mx plus b and then replaced y with whatever's on the y-axis. That's 1 over di. Replaced x with whatever's on the x-axis, 1 over do. And then I changed the m to a slope, and I did that only because I don't want to get the slope mixed up with mass. What's next? What's next? This is the equation that comes from my graph. What do I do after I have that equation that comes from my graph? Yeah. Good. Let's get one on our data sheet that has 1 over di and 1 over do in it. That equation for my data sheet is going to be 1 over f is equal to 1 over do plus 1 over di. Now I want to rearrange that to take the same form. So let's solve for di. Sorry, not for di, but 1 over di. Let's take the 1 over do over to the other side by subtracting. I end up getting 1 over f minus 1 over do equals 1 over di. Make sense? Well, it still doesn't look exactly the same. So let's just swap places here. Let's say 1 over di is equal to negative 1 over do plus 1 over f. That's the same thing, and that's better because it takes the exact same form as the equation that I have up here. 1 over di, something times 1 over do, and then we've got b being the y-intercept or 1 over f there. Let's start crossing things off from equations that appear in both, the one from the graph and the one from the equation sheet. 1 over di appears in both. 1 over do appears in both. We're left with slope is attached to 1 over do. Negative 1 basically is attached to 1 over do. So we're going to say the slope in this case is simply negative 1. In this case, we're going to say the y-intercept, b, is 1 over f. If you get a question with these variables on there, you're probably going to use the y-intercept to get whatever you want to find. In fact, it'll probably be the focal length. If you get another graph, maybe it's the slope that you need to use, because usually the slope works out not to be a number, but an expression. For instance, we did the example on Friday, d versus t squared. The slope ended up being equal to 1/2 of the acceleration. If we wanted to find the acceleration, then we calculate the value of the slope and then just rearrange it to solve for the acceleration. If in this case we want to find the focal length, then let's get the y-intercept by reading it off of the graph and then just taking the inverse of it to get the focal length. Do you remember that from Friday? On Friday, you guys told me that it was making a lot more sense than the 4 or 5 examples that we did earlier in the year, as we did one, kind of at a time. Is it ringing a bell? You're going to see one of these questions on the test, so let's let's be good with it. If you're not, then make sure you ask questions. Make sure you come and see me and get some help on it, because you're going to see one. It's one question out of 49. Sorry, one question out of 50, which doesn't sound like that much. It's 50. That's 2% of your diploma exam, which is 1% of your overall grade, Physics 30, for a graphing question. We know what to expect. We know we're going to get one. Sometimes it's harder than others, but if we understand this, at least we've got a fighting chance at it. All right, what I want to do today is this new type of numerical response question that's appeared for the last year and a half or so. New type of numerical response question, I'm not a real big fan of, to be honest, but it is what it is. A year and a half or so ago, they took away the written response component of the exam. It used to be 65% multiple choice and numerical response, and then 35% written response. So in your written response, a lot of people didn't do all that well in the written response, but I liked the written response because it gave you an opportunity to show your thought process, and not just, A, B, C, or D. Oh, you got that one wrong, it's 0 to 1. It gave you a chance to show thought process. Now they don't have that, but they replaced it with a new type of numerical response, which is supposed to show this thought process, but I don't really think does a very good job at it. The new type of numerical response is the type that you see in every question but one in the booklet that I just gave you. I don't want to do the first question first. Just happened to be the one that was in my booklet on the front here. What I'd like to take a look at first is the second question. Forget about the information that it gives you there right now. Just look at the questions at the bottom. It asks you for the two physics principles required to determine the instantaneous acceleration, and it asks you for the value of the instantaneous acceleration. I don't have a problem with them asking you for the value of the instantaneous acceleration. That's a numerical response question. But I do have an issue with them asking you for those physics principles, because I think although in a way it shows process, I think more than anything, it just confuses people. I don't think it has to confuse people, but I think it does sometimes. We're going to focus on this particular type of numerical response today so that you're able to answer not so much the second question, because that's the content of Physics 30 that theoretically you know how to answer already, although these tend to be tough questions. Rather, I want to focus on that first part of the question, okay? The physics principles. The reason I want to do that is because A, you're not so familiar with that, but B, even if we have a really tough question, which we often do in this type of numerical response question, you can often answer the physics principles without actually doing the question correctly. You can get the question wrong and still get the two physics principles and get that portion of the question correct. Okay, so as much as I'm not a big fan of that question, it can be almost a gimme. The first part of it, not the second part of it, but the first part of it can be almost a gimme. They list 10 physics principles in that question. Those 10 physics principles will not be listed with the question on your exam. They are listed where on your exam? Data sheet. Bottom left-hand corner of your data sheet. I'd like everybody to open up their data sheet right now to take a look at that so you know where they are. The first physics principle, bottom left-hand corner of your data sheet. Remember, we're doing this specifically for the second question in this numerical response booklet, but it applies to all of them. It applies to all of the questions in this booklet. The first principle says uniform motion. Then it says in brackets F net is equal to 0. On your data sheet right now, please write this in. V is equal to delta D over delta T. Write down V is equal to delta D over delta T, or just D over T. If you use this equation, if you're going to use this equation in your analysis of the problem, then that physics principle applies, uniform motion. Because that's what uniform motion is, constant velocity. the net force is equal to 0. Okay, V is equal to delta D over delta T. The alternative thing that you could be doing and still be uniform motion, actually it wouldn't be, because it would be motion or an object at rest. I was going to say forces are balanced. Yeah, forces are balanced, but not in the sense that it's suspended, because that's not uniform motion anymore, right? That's not moving. If something's has balanced forces but is moving, then that applies. But of course, that ends up being V equals delta D over delta T as well, if it's moving at a constant speed. So the first principle, principle 0, if you use this equation, then you're going to write down principle 0 as your physics principle. The second one is accelerated motion. Accelerated motion, it says F net is equal to something other than 0. Basically, if you use any of those acceleration equations, A is equal to delta V over delta T, D is equal to VIT plus 1/2 AT squared. Any of those acceleration equations that you learn in Physics 20. Anything with A in it, but you got to be careful with that, Braden, because here's one. D is equal to VIT plus VI plus VF over 2 times T. You learned that in Physics 20. That's an acceleration equation, but it doesn't have acceleration in it. Any of those equations that are valid for acceleration, then the physics principle you used was accelerated motion. Principle number 2, that one's really relatively straightforward. Uniform circular motion. Basically, if something's going in a circle, then it's uniform circular motion. You might use the equation A is equal to V squared over R. You might use the equation F is equal to mv squared over R there. Remember that one actually doesn't appear on our data sheet, so you might have to remember that one. If you use any of that, then you're using uniform circular motion. 3, the work energy theorem. If you're assuming that the work done is equal to the change in energy, then you're using the work energy theorem. Principle number 4, it says conservation of momentum. Well, that's an easy one. If you're doing PI is equal to PF, that's conservation of momentum. And when do we do that? When we have a collision or an explosion. Principle number 5, conservation of energy. EI equals EF. Maybe we're going to do MGH equals 1/2 mv squared. Maybe we're going to do QV is equal to 1/2 mv squared in the case of a charged particle speeding up. Both of those are conservation of energy. So if you do any of this, then you're going to use principle number 5. Principle number 6. Conservation of mass energy. Tell me, what equation would I have to use in order to say principle number 6 was one of the principles I used to solve the problem? One simple equation. E equals mc squared. If I use E equals mc squared, then I've used principle number 6. Conservation of charge. That's not so much an equation. Conservation of charge is when the total charge hasn't changed. It's not increasing, it's not decreasing, when it stays the same. When do we use the law of conservation of charge? A lot of times we use the law of conservation of charge when we're maybe doing charging by contact, and we're trying to see what the charges balance out to be. Okay, maybe we're, where else would we use the law of conservation of charge? Charging by friction, trying to find out what the charges end up being. Maybe we're talking about beta decay. Remember, beta decay involves, beta minus decay involves a neutron changing into a proton and an electron. Well, the law of conservation of charge applies there because we had a total charge of 0. We've got to get the electron produced as well to keep a total charge of 0. So the law of conservation of charge would apply there. Not so much in an equation, but still conceptually, it sometimes applies. Conservation of nucleons. What's a nucleon? A nucleon is a proton or a neutron. So conservation of nucleons would apply when we have a nuclear equation. Right? We're trying to balance a nuclear equation. And principle number 9, wave-particle duality. If we're looking at the wave nature of an electron and the particle nature of an electron, that's wave-particle duality. If we're looking at the wave nature of light, V is equal to F times lambda, the wave nature of light, and the particle nature of light in the context of the photoelectric effect, that's wave-particle duality. So if we're looking at a wave or a particle from both aspects, that's going to be wave-particle duality. I would suggest the further down the list we go here, the less often we use these principles in terms of a problem like this. Okay, I'm not saying that it's impossible to ever get principle 7, 8, or 9, but it's less likely to get 7, 8, or 9 than it is to get 0 through 6, or even 0 through 5. You know why they start at 0 instead of 1 through 10? They used to be 1 through 10. And then after the second exam of being 1 through 10, they switched the principles, renumbered them 0 through 9. If you take a look at that question, that second question in the booklet, they're all formatted essentially the same. They want you to list the physics principles that you used. And there's always going to be 2 of them. There's 4 boxes. They want you to list 2 principles. Well, if I use principle 7 and principle 2, it's all good. If I use principle 6 and principle 10, all of a sudden it becomes a 3-digit answer. So if they tell you to express your 3-digit answer, they're telling you that one of the principles was the last principle. So they switched it to 0 through 9, so it's always going to be a 2-digit answer now, always. Does that make sense? Always going to be a 2-digit answer. All right, let's take a look at this question, this second question from the booklet that I handed out to you today. We'll solve the problem. Forget about the physics principles right now. We'll solve the problem. If you're not able to solve the problem, then you got to look at the physics principles still. But if you're able to solve the problem, then looking at the physics principles should be easy after that. So that's what we'll try first. Then we'll go back and answer the first question, 263, that addresses the actual physics principles as opposed to the numerical value of the answer. Braden? Forget? All right. Question 263 says, and you can see it in front of you right now, says electrons are accelerated from rest by an electric potential difference of 300 volts. Right now, without even looking at the answer key, right now I see that first sentence, and I think I know one physics principle that I'm going to use already. Which principle am I going to use already? Uniformly accelerated motion. Could be. Could be. That's not the one that I was thinking of, to be honest. It is accelerating, so that one would definitely apply. That would be definitely a valid answer to put. There is often more than one option, by the way. Sometimes they'll say there is more than one possible answer to this question. Okay, that's not the one that I was thinking of, Braden, but yours is equally as good as the one that I was thinking of. Okay? Conservation of energy was the one I was thinking of. What do we do every time a charged particle speeds up? EI equals EF, conservation of energy, right? So that would be principle 6. Now, Braden, you said principle 2, which was uniformly accelerated motion. Kai said principle 6, which is conservation of energy. We're probably not going to do both of those. It's one or the other. So you can't put 2 and 6 as your answer. Does that make sense? You're going to put 2 or 6, and then you're going to put some other principle that you end up using as well. Okay, let's read the rest of the question here. Braden? We'll deal with that when we get to it. Yeah, we'll deal with that when we get to it. The electrons enter a region that contains mutually perpendicular electric and magnetic fields. The electric field has a magnitude of 8.5 times 10 to the 5, and the magnetic field is 2.0 times 10 to the negative 1. And you can see in this diagram, right, it's accelerating across this potential difference of 300 volts. We've got this positive plate up here and a negative plate down here. We've got these electrons going this way in a magnetic field that is into the page. We want to know the value of the instantaneous acceleration experienced by an electron as it first enters the region. Okay, we want to find the acceleration in here as it first enters that region. It's a tough question. Since they started putting this format of numeric response on there, again, on each exam they only put one question where you have to solve for, and then the corresponding question where you have to list the principles, one of each. They have been hard questions except for once. Once I would say it was a really easy question. The other times they're pretty tough. Okay, but they're doable, usually doable. How are we going to analyze this? Well, we know every time from almost the beginning of Physics 20, if we've got more than one force acting on an object, what should we do? I'll give you a hint. We should draw something. Draw a free body diagram. In this case, we have two forces acting on this electron. We have an electric force acting up, and we have a magnetic force acting down. If we do the hand rule, thumb, fingers, palm, the magnetic force acts down. Now, do those two forces balance each other out this time? No, they don't. So we know that it's not going to be principle number 1, uniform motion, right? Because it's not uniform motion. It's accelerating here. We know that the electric force has got to be up, the magnetic force has got to be down. What did we do way back in Physics 20, and some in Physics 30 as well, when we have these two forces that don't balance out? Christian? Yes, good. F net is equal to the sum of the forces. F net is equal to FE plus FM. Now we also know that F net, the total force, is M times A. So Braden, as I start doing this, it's actually looking like I'm going to actually solve the problem using the method that you suggested. And that was the uniformly accelerated motion, principle number 2. Hey, Kai and myself both chose principle 6, but in the end, I don't think we're going to end up using that. If we wrote it down, we could still get credit for it because it's a correct method. It's just not the most convenient method, I think. The most convenient method is what we're doing right now, which, Braden, is what you suggested. The electric field or electric force is Q times E. The magnetic force is QVB. Let's plug in some numbers here. The mass of the electron is 9.11 times 10 to the minus 31 kilograms. The acceleration is what we're looking for here. The charge is 1.6 times 10 to the minus 19 coulombs. The electric field is 8.5 times 10 to the 5 newtons per coulomb. Is the electric force positive or negative? Positive because it's acting up, so we won't change anything there right now. Plus QVB. The charge there is, again, 1.6 times 10 to the minus 19 coulombs. The speed of the particle. Do we know the speed of the particle? It's accelerated through a potential difference, and then it's going into this electric and magnetic field where it kind of curves downward. Do we know the speed of the particle as it goes through this electric and magnetic field? Go ahead. No, that would be the electric force toward the positive. If you've got a negative particle, it experiences a force opposite to the field, or it's attracted toward the positive. But the magnetic force is given by the hand rule for deflection. So we'd say thumb in the direction of the particle, which is to the right, fingers into the page, because that's the direction of the magnetic field, palm points downward. Got it? Do we know the speed here? We don't know the speed. But we do know that before it got to this section over here, before it got here, it went through this potential difference. We're going to go back to what I thought after all, and what Kai thought after all, and that's EI is equal to EF. Let's look at the first chamber. We've got electric potential energy. That gets converted to kinetic energy. Let's solve for the speed at the end of that section. 1.6 times 10 to the minus 19 coulombs gives me my charge. The potential difference that it goes through is 300 volts. That's equal to 1/2 of 9.11 times 10 to the minus 31. The mass times v squared. We'll solve for the final speed of this electron. It works out to be 1.0265 times 10 to the 7 meters per second. So at the end of this section right here, it's traveling at 1.0265 times 10 to the 7 meters per second. When it enters this section right here, it's traveling at that same speed, 1.02 times 10 to the 7 meters per second. Is that magnetic force up or down? Down. So let's make it a negative value. I don't care whether you put the negative in front of the 1.6 or in front of the 1.02. Either way gives us a negative force or a downward force. Let's do the math on that and we'll solve for the acceleration. When we do, it works out to be negative 2.11 299 times 10 to the 17 meters per second squared. We're going to round that to negative 2.11 times 10 to the 17 meters per second squared. The question asked me, the second question there, within that second question, so 264 on that booklet that I photocopied for you, we want to know the instantaneous acceleration as it enters the region containing the perpendicular fields. Blank times 10 to the W. What's the answer to 264? 2.11. That's a tough question. There are harder questions, but there are definitely easier questions. That's a tough question. Braden? Sorry? Oh, did we have the value of the magnetic field? Yeah, I think I did actually. But yeah, it's 0.2 Tesla. But that's still the right answer. No, because they're only asking you for the magnitude of the force. Actually, they're not. If this is a real test question, though, they would say the magnitude of the acceleration as opposed to the instantaneous acceleration. You'll never have to put a negative in because there's nowhere to put it in a numeric response, right? They could, yeah. Yep. They might say negative blank times 10 to the W. Now, what two physics principles did I use? Let's go back to the list that we kind of looked at a few minutes ago. What did I do right here? What principle is that? Which one is it? It's principle number 1. Let's just, wherever you show your work, okay, on a piece of scrap paper, whatever, let's just write down principle number 1. Don't worry about the order that you did it in yet. What do we do over here? Nope. It's not 5. It's principle 6. Okay. Oh, it is, yeah, sorry. Yeah, sorry. It's, yeah, on your data sheet. We'll go with the ones on your data sheet. So scratch those numbers out. I didn't notice that they were different, actually. Scratch those numbers out on the booklet that I gave you, because those aren't the numbers that they use now. The numbers that they use now are 0 through 9. So we used uniformly accelerated motion, which was principle number 1, and we used conservation of energy, which the new numbering system is principle number 5. So the answer to that first part of that question would be what? 1 and 5. They used to require you to do it in order. So 1-5 or 5-1, there was a right answer and there was a wrong answer. Now they don't care. So now if you write down 1-5, you'll get it right. If you wrote down 5-1, you will also get it right. on your data sheet. We're going by your data sheet. It's principle 1 and 5. Because those are the numbers that should be on your test. Check that. Make sure that the data sheet is exactly the same. The last time they pulled that, they switched the numbering system on there. The data sheet was otherwise identical, but they didn't tell us as Physics 30 teachers that they were switching the numbering system. Wasn't a huge deal, but if you were used to saying conservation of energy was principle number 6, all of a sudden on that exam it wasn't principle 6, it was principle 5. So just make sure that everything is the same. Should be, because they haven't told us otherwise, but just make sure it is before you go and pencil something in. By the way, make sure you start on the left-hand side. Instead of starting on the right-hand side, should be good to go. It's hard to believe, but it's 4% of your diploma exam right there. That's 2% of your overall Physics 30 mark right there. Now, what if you can't get this? Hey, Kai said principle 5, you said principle 1. You write those down before you did anything. If you had written those down, and you would have gotten that question correct. Well, you might be able to, hopefully you can figure it all out and get the whole answer, right? But if you can't, then at least write down the physics principles. All right? Let's take a look at another one. Should we take a look at 265? It's a toughie. Should we do that? You know what? Let's do 269 actually. It's a tough one as well. They're all tough ones in here actually. I picked tough ones to put in there on purpose. 269 is a little bit quicker for us though. $269, you get this thorium-226 in a lead box. It's decaying and it's producing alpha particles. And these alpha particles are leaving this lead box and going towards this positively charged plate. It says the nucleus of thorium-226 is... Says the daughter nucleus produced radium-222 has a mass of 3.67 times 10 to the negative 25 kilograms and moves to the right immediately after the decay. The thorium-226, the radium-222, and the alpha particle form an isolated system. That word right there, they tell me it forms an isolated system. That word right there, I mean, I've done this a number of times, not this particular question, but Physics 30 enough times, that word kind of jumps out at me. When I see something that says an isolated system, right away I think conservation of momentum. And as much as in nuclear decay courses, we don't often do conservation of momentum in that context. We don't often do it in that context. It definitely applies because we've got one thing becoming two things. It's like an explosion. And the reason that I think that we're going to use conservation of momentum on this isolated system, why else are they telling me it's an isolated system? We have to have that isolated system for conservation of momentum to apply. Why would they be telling me it's isolated if conservation of momentum wasn't going to be used here? We'll see. I mean, we'll see. To the left of the lead box are two parallel plates, one positively charged and the other negatively charged, that together produce a uniform electric field. The parallel plates are 2 centimeters apart. The escaping alpha particles are stopped by the electric force just before they reach the positively charged plate. The complete apparatus is in a vacuum. So it looks like kind of an ugly context here. Let's forget about 269 for a second where it asks for the two principles. Let's just go straight to 270. What's the magnitude of the electric force acting on the alpha particle? What's the magnitude of the electric force acting on the alpha particle? Well, right now, as I read that, conservation of momentum doesn't seem to be as high on the list of things that I might want to try. Right, clearly, I'm looking for an electric force. I'm probably not going to start off with conservation of momentum. Who knows down the road, but let's deal with the electric force portion of this first. Excuse me. We know we want to find the electric force acting on this alpha particle between the two plates. We have 3 equations for electric field. 2 of them are valid between parallel plates. We have E is equal to F over Q, which is the electric field acting on any particle, any experiencer. And we also have E is equal to delta V over delta D. That's the electric field between 2 parallel plates. Now, my gut feeling on this since I'm looking for electric force, and I'm not dealing with the electric force between two charged particles, is that I'm going to use this equation. E is equal to F over Q. Let's try that. Let's rearrange it. F is equal to Q times E. Well, excuse me. The electric force is Q times E. The charge of the alpha particle is 3.2 times 10 to the minus 19 coulombs. The electric field, we don't know. So let's see if we can find the electric field. We know that E is equal to delta V over delta D applies to find the electric field. Do we know the potential difference between these plates? We don't. Any suggestion as to how I might find the potential difference between the plates? What's happening to the alpha particle when it goes between them? It's entering the plates and it's decelerating. It's slowing down and coming to a stop. What do we do when charged particles slow down? I know Kai knows this because he basically answered the question for the last one. What do we do when charged particles speed up or slow down? Conservation of energy, right. EI is equal to EF. In this case, it's actually slowing down, so we're going to say 1/2 mvi squared equals QVF. So we're not talking at the beginning of the problem that it's 1/2 mv squared. We're saying when it enters these plates, it's 1/2 mv squared. Let's plug in our numbers. The mass of the alpha particle is 6.65, I think, times 10 to the minus 27. We don't know what VI is. And we can get V, plug it into there. We can get E, plug it into there, and solve for force. But we don't know what VI is. Anybody suggest how we might find the speed as it enters these parallel plates? Well, let's use the whole nuclear decay thing. We had a nucleus that breaks up into an alpha particle and something else. How can we find the speed of an alpha particle that's emitted from radioactive decay? Radioactive decay is like an explosion, conservation of momentum. Let's try that. Look at stuff all over the place here, right? Before the explosion, the total momentum is 0. Afterwards, it's m1 v1f plus m2 v2f. m1, let's say that's the alpha particle, 6.65 times 10 to the minus 27. We don't know what v1f is. The mass of the other particle, we're given that value as 3.67 times 10 to the minus 25 times the speed of the other particle, which is 3.10 times 10 to the 5 meters per second. Solve for V1F. When the alpha particle leaves this lead box, it's moving at a speed of 1.710827 times 10 to the 7 meters per second. Let's take that number and plug it in here. Let's solve for VF, which is really the potential difference. It's the same thing as the potential difference. It becomes 3.041262 times 10 to the 6 volts. Let's take that number and plug it in up here for the potential difference and solve for the electric field, which is 152063121.5. And then let's take the value of the electric field and plug it in for the force. When I solve for that, it works out to be 4.87 times 10 to the minus 11 newtons. That's my final answer. Now, how do I express this? They want the value, just the simply the base of that answer. So we would express that as 4.87. Now, what about the two physics principles that we used? Let's go through this entire problem and try to identify in every step what physics principle we used. Pi is equal to Pf. What principle is that? It's conservation of momentum. What principle is that? Principle 4. Okay. EI is equal to EF. That's conservation of energy. That's principle 5, I think it was. EF is equal to Q times E. I would say we could classify that as unbalanced force. Right? There's a net force there. So that would be principle, or uniformly accelerated motion, I should say. That would be principle 1. This one doesn't really fit in there. They'll often say there's more than one possible answer. So in this case, there are a few possible answers. You could say principle 1 and principle 5. You could say principle 1 and principle 4. Or you could say principle 4 and principle 5. And it doesn't really matter what order you put them in. Any of those three work. Does the whole physics principle thing make sense to us there? Okay, secondary to that, does the question make sense? This is a tough question. Does it make sense? It's a doozy, yeah, it's a doozy for sure. And I'm not going to lie to you guys. There is a good chance that when you get this numerical response question on your exam, that it will be a doozy. It's not always a doozy, but more times than not, it is. But we still have a chance at getting the answer correct. We have a real good chance, I think, at getting the physics principles correct. I mean, think about that. Like, let's say I can't answer this question. I don't know how to do this question exactly. But the first thought that I had come to my mind was conservation of momentum, because I saw the word isolated system. And then we saw the charged particle was slowing down. And right away I thought conservation of energy and conservation of momentum. I didn't know anything about what to do with them. But I still knew those two principles, and I would still get this question correct as a result of that. All right?